Hello, everybody. Welcome to my talk. Today, I am going to share with you my takes on quantum-resistant healthcare. My name is Katarina Amrichova, and currently, I am a cybersecurity researcher in Siemens Healthineers. I have been working for Siemens Healthineers for 4 years now. However, my very beginnings of meddling with the computers date back to early 2000s, when I was 3 or 4 years old and I was just playing this game of Aladdin on an old Windows 98 machine, and I was talking to Clippy whenever I got a chance. And I still do talk to him today. I have him 3D printed on my desk, and he's the best debugging buddy. But on a more serious note, how does one transition from being a child, meddling with computers, playing computer games, to being a cybersecurity researcher? Well, it has been a long journey, but the most significant part of it has happened in the past couple of years when I joined Siemens Healthineers, and I started working there as an ethical hacker. I was focusing on reverse engineering. And then in my free time, I did some research and I did a presentation. I got accepted at a conference and the company noticed. And they gave me this perfect role of being a cybersecurity researcher and doing the research I like. And the first topic that I was looking into was actually homomorphic encryption. That is a very cool technology, and if you have time, check it out. For me, it's the holy grail of cryptography because it gets you perform computations on fully encrypted data. However, it is more in the research world and it is not as production ready. But post-quantum crypto is much more production ready, and this is why I started studying this topic, because it is something that we could use to improve the company's products nowadays. And it is getting more and more traction because everybody is trying to calculate when the Q-day will come, when a cryptographically relevant quantum computer will be there. And also regulatory push is big towards transitioning to post-quantum crypto. But the thing is that not all of the cryptographic algorithms that we are using today would be threatened by a quantum computer. So actually, only the symmetric algorithms, the hashing algorithms and SHA, AES, etc., those would not be threatened by a quantum computer because of course, there's Grover's algorithm that could speed up their cracking, but it would be enough to double the key sizes, and it would work. It would be secure. However, the asymmetric algorithms, which we are using for TLS connections and for certificates, this is something that a quantum computer could potentially break. And that is a problem. And the biggest problem is the harvest now and decrypt later type of attacks, because if the attackers get hold of a quantum computer many years from now, for example, 10, 20, 30 years from now, they would be able to retrospectively decrypt all of the communication they intercepted. And that is a big problem because the information that you are sending over the internet today, you might still want to keep it confidential many years from now. And this graph shows the risk of quantum-powered attack sorted by industry. There are two variables used in this graph. One is data shelf life and the other is system life cycle. And the longer the data shelf life and the longer the system life cycle, the bigger is the risk. And this graph basically shows the industries which are under the highest risk in the upper right corner and the ones that are in a slightly lower risk in the bottom left corner. And it also shows different medical devices. So in my opinion, big modalities, big medical devices, such as MRI, CT, X-ray, ultrasound machines, those should do the transition as the first ones, because those are at the highest risk, because their system life cycle is really long. And if you have some MRI machine and you sell it to a hospital today, chances are that it might still be used maybe 30 years from now, maybe even 50, at least in Slovakia, where I come from. I'm not sure how it's around here. And then you have the smaller devices, the chemical analyzers, the blood pressure analyzers, patient monitors, etc. And those devices are at a slightly lower risk because they have a slightly shorter system life cycle, but they still deal with sensitive patient information. So you still want to protect them. And the medical software, I think the risk is the lowest there because the system life cycle is not that long. And you might be asking when the Q day will come, when we will have a cryptographically relevant quantum computer. And there are many guesses out there. I don't know the answer. I just use one of the resources, and this shows the extrapolation of the rising number of qubits. So the full red line shows the historical data, how the number of qubits has been rising steadily over the years. And the dotted lines show the extrapolations. So the blue dotted line shows the optimistic extrapolation, and the green dotted line shows the pessimistic one. And by the way, I would like to point out here that the scale is exponential. On the y-axis, it is not linear. So really the number of qubits is rising rapidly. And the number of qubits that would probably be needed to break 256 bits long elliptic curves is estimated to be 1 million. The number might change if the error correction gets better over the time, but the best guess at this moment is that it will be 1 million physical qubits. And there is a difference between a physical and a logical qubit. So usually a couple of qubits, maybe around 100 physical qubits make up one logical qubit. So 1 million physical qubits, and chances are that we might reach that point around 2040. Maybe earlier, maybe later, who knows. But the regulatory bodies are starting to react to that. And CNSA 2.0 already contains post-quantum crypto algorithms, or PQC, that's the abbreviation. So CNSA 2.0 already contains PQC algorithms, and CNSA 2.0 should replace CNSA 1.0 and Suite B cipher suits. And Suite B cipher suits, that's something that FDA requires medical manufacturers to have and to fulfill. So chances are that in a couple of years, maybe FDA would start pushing towards the transition to PQC as well. And the medical manufacturers would have to react to that. And this is why we started thinking about this problem in Healthineers, and we created this transition timeline with different steps and milestones which should be achieved. And of course, the first one is spreading awareness, and you need to spread awareness internally and externally, because all the involved parties need to be aware of PQC and of the risks that quantum computers bring. All the developers and the project managers, the cybersecurity personnel, they need to know what is waiting for them and what problems they will have to solve in the future. And also third parties need to be aware, because sometimes we are using third-party dependencies where we cannot really influence what crypto is being used. So those negotiations should start happening, and we should start talking about this topic with the third-party suppliers as well. And now let's get to the most interesting and technical part of the talk, in my opinion. That's the milestone number 2, implementing a prototype, implementing a proof of concept in one of the products. And this is something that has to be done because one never knows how PQC will interact with the environment, with other products. I know that Google and Cloudflare have been experimenting with PQC a couple of years ago. Actually, some browsers already do support PQC. Also, Signal Messenger. I think Meta is doing some research, etc. So there is some support of PQC out there, and but in the very early years when they were experimenting with it, Google and Cloudflare found out that 30% of their communication was failing. And the reason was that PQC has large keys. And those keys simply didn't fit into one client hello and server hello. And it had to be fragmented into multiple packets. And the middleware didn't know what to do with that. The middleware just started throwing away those fragmented packets. So routers, switches, throwing away all those fragmented client hellos and server hellos. And this is exactly the reason why we need to do these sorts of prototypes, because we need to know how PQC will change up our environment, and we need to have remediations, fallback plans for that. And that is the reason why I did this proof of concept, where I put PQC into a secure DICOM communication. So I basically programmed a server and a client which were able to communicate with each other over DICOM protocol, and the whole communication was wrapped in TLS, and I added this PQC component into that. And the DICOM protocol, or the DICOM layer, was implemented in the DCMTK library. The TLS layer was implemented in the OpenSSL library. And then the PQC parts were implemented in the OQS provider and libOQS. And OpenSSL has a very nice support of the PQC handshakes. However, the DCMTK doesn't know what to do with it. So DCMTK expects OpenSSL to be used in its vanilla version. And it isn't counting with using any provider at all. So this is why I had to change some parts of DCMTK. Fortunately, it was not too many, just adding a few lines of code, but I had to identify where to put those changes. And after I changed up those things and I added OQS provider into DCMTK library, I did a DICOM communication. There is a DIMC send echo request and send echo response. So that's the DICOM protocol. And on the second side of the screen, there is a Wireshark capture. And that Wireshark capture shows the server hello, and it shows that key share entry is Kyber 768. And that's a post-quantum algorithm. So, actually, I would probably, now that I'm looking at it, I would use a hybrid and maybe a slightly stronger algorithm. So not really Kyber 768, but something with a longer key size, and also hybrid, because those PQC algorithms are quite new. And even though there was extensive cryptanalysis performed on them, we still aren't sure if they don't contain any errors, because they are quite new. They haven't been around for 20, 30 years, such as the other algorithms that we are using today. That's why the hybrid approach is a good one. But this, what you are looking at, might be one of the first PQC secure DICOM exchanges ever. And after that prototype, there is another point, or another milestone that I want to talk about, because having prototypes is nice. But if you are a healthcare vendor and you have like tons of software, you need to prioritize which parts of software you should transition to PQC as the first ones. And for that, you need to be aware, you need to know what cryptographic algorithms do you actually have inside of your software. And that's why you need a good CBOM. CBOM sounds similar to SBOM. SBOM means software bill of materials, and CBOM is crypto bill of materials. So CBOM basically lists all the cryptographic algorithms used inside your software. And if you have a good CBOM, then you can use it and perform a threat and risk analysis on top of it. And you can prioritize the transition process of your software. However, it is challenging to build a CBOM because there is no tool readily available for it. There are some tools, but their coverage is limited. And in order to have a good CBOM, you need to connect two capabilities. One is SAST capability, or static software analysis, static code analysis capability, and the second is SCA, so software composition analysis. Software composition analysis is what gives you those SBOMs, what gives you the list of dependencies. And you need SAST capabilities because you need to really look into the source code. You need to really understand which algorithms get invoked in the source code. However, the crypto can be hiding anywhere in the dependency tree. And that is why you need also the SCA capabilities and why you need to build this dependency tree and then also scan those third-party libraries to identify what crypto is hiding in them. And you can do it, of course, only with the open source libraries. With the closed source, you would need to notify the vendor. With those SAST capabilities, we can use the existing SAST rules, SAST queries, but we need to enhance them and rework them. Because the existing SAST rules are built to detect software vulnerabilities. They are able to detect vulnerable crypto being used, but they are not able to detect all types of crypto being used. And you cannot just write a simple grep to get this answer, because different libraries in different languages work in a different way. They might have slightly different naming conventions. So you really need to fine-tune your rules to find what you need. And this is why we did this second proof of concept for building CBOM, for building cryptographic bill of materials. And we basically prepared one Azure pipeline, which is communicating with open source tools, with Sonar Crypto plugin and with CBOM kit. And those tools are developed and open sourced by IBM Research. And actually, we are helping IBM Research develop it further and add new features, increase the coverage of those tools. I recently got a working student who is working on his bachelor thesis, and he was helping me out with this stuff, with the pipeline and also with increasing the coverage of the Sonar Crypto tool, etc. And what this pipeline is doing, it can be divided into two parts. First is scanning the project CBOM, so the code that you have in your repository, scanning through it and identifying the crypto used. And second part is generating the list of dependencies and scanning through those dependencies. And basically in the first step, the project is built and it is sent for analysis to SonarQube. We have our instance of SonarQube where we installed experimentally this Sonar Crypto plugin. But the Sonar Crypto plugin supports only Java and Python at the moment. And within those languages, it supports detection of just a couple cryptographic libraries. So the crypto library within Python, and then Bouncy Castle and JCA in Java. And in the future, we would like to add support of more languages and more libraries. C# would be the best choice. So C#, maybe some C and C++ detections would be good, and also adding support to another libraries. It is a tedious process to write those detection rules, and especially the support for new language can be really difficult. So far, we only increased the coverage for Java, and we are able to detect some crypto invoked from a Tink library, which is a library released by Google. We are working on increasing that coverage. And back to the pipeline. After the project is scanned and the CBOM is generated, then what we do is that we store that CBOM in the CBOM-kit database. And after that, we jump to the second part of the pipeline, so looking at the crypto of third-party dependencies, where we generated the SBOM, we generated a dependency list, we parse that SBOM for PURLs or package URLs, and we check if a CBOM for that specific package has already been generated or not, because we don't want to do that work twice. So we just communicate with the CBOM-kit database. And if we get an answer that it isn't existing in the CBOM-kit database, then we invoke a scan for that PURL, and we generate a CBOM for that new third-party dependency. However, some features in CBOM-kit are still missing because there is no project management inside CBOM-kit at the moment. So everything just gets into one place, and we would need to add that feature. That is one of the possible follow-ups on that. One of the possible future directions. So adding the project management, the user management, etc. So back to the to the timeline, we have covered those two proofs of concepts. One for implementing a prototype in a Healthineers product, second for generating a CBOM and performing a threat and risk analysis. And now the fourth step, or the next step, would be to prepare some sort of documentation for it, because we would like to really see these things being used internally. So it has to be somehow imposed on the development teams. There has to be some strategic document, some directive, some guideline, which would require the business lines to use the service for generating CBOMs, to perform the threat and risk analysis with quantum threat in mind, and to start performing those transitions. However, we cannot do that if the tools that are out there that we are suggesting are not mature enough. So that's why we need to iterating over the step 2 and 3 and really making sure that we are increasing the coverage. And once we get to a sufficient point where we are satisfied with what the tools can do, and then we can start requiring it. And also the language support is an important thing because currently OpenSSL supports PQC quite nicely. In November, there will be .NET 10, which will also support PQC natively, which is very nice, but they will support only the PQC primitives. They will not support PQC on the TLS layer yet. At least that's how I understood what I read so far. So we would still need to wait until that language support is more extensive in order to start requiring it from the business lines and from the different projects inside our company. And the last, final, and ultimate goal would be to have PQC implemented in multiple Healthineers products and to actually have some medical devices with PQC in it on the market. That would be the ultimate goal of this initiative. So thank you for your attention. And if you have any questions. Thank you. If you have any questions, feel free to ask them now or catch up with me later when I get off the stage. Yes?
Do you see it being a huge problem backporting? Because in this space, we have devices out there for them. So from my neck of the woods says the biggest thing for us is, we're developing products that are still going to be out there in 2045 probably. So how do we work around that? And what have you kind of thought about that subject?
Maybe using some sort of wrapper or an intermediate network layer would be a good approach that would just intercept all the, it would be like on the medical device if we are talking in medical devices, and it would intercept all the TLS communication going out and change it to PQC communication, and that could be an option. Yeah, that was just my chain of thoughts, but I haven't been exploring it in depth. Thanks for the question. Yep.
It's exciting to see this work and actual implementation work. I appreciate you sharing that. I always think about this topic in terms of confidentiality and authentication. Correct me if I'm wrong. This was deploying your implementation a little bit. It was deploying the confidentiality to the establishment between it, as opposed to the authentication. We're adding PQC-based digital signatures, which is the same as what Cloudflare. I just want to make sure that I understood that.
Yes, you understood that correctly. Actually, that's a very good point. I should have pointed that out. So I was focusing just on the CAM, on the key exchange, because I think that it is a more pressing issue, because CAM protects you against a passive attacker, while the signatures, they protect you against an active attacker. And because of those collect now, decrypt later types of attacks, we need to focus on protecting against passive attackers, so using the key exchange, quantum secure key exchange. And then once there is a cryptographically relevant quantum computer built, then also that signature part, the authentication, would be a more pressing issue in TLS. Yeah.
I intuit from your answer that it's down and out of it.
Yes, because currently there is me and the working student working on it, so we decided to narrow down the scope and take care of the signatures later and certificates. Yeah. Thanks for the question.
So wrapping the PQC in the TLS connection to deal with fragmentation sounds to me like an ungraceful way to handle the problem. Do you see that as a temporary measure, like in future years we'll have different protocols though?
Well, actually, TLS 1.3 standard is already supporting PQC. So that problem with Cloudflare that I was talking about, that was probably before TLS 1.3, I think. I'm not 100% sure about it, but it is already, PQC is already being included in those new protocols. Yeah, thanks. Okay, any more questions? Okay, in that case, thank you for your attention. That's it for today.